Concrete is the second most consumed material on Earth, trailing only behind potable water. We use it to build everything from skyscrapers to the sidewalks under our feet, yet it hides a fatal weakness. It is inherently brittle. As a concrete structure shrinks and expands over time, tiny, almost invisible fissures form. These microcracks act like open wounds, allowing rainwater, aggressive chemicals, and road salts to seep deep into the core of the material. When that moisture reaches the embedded steel reinforcement, a destructive chemical reaction takes over. The steel begins to rust, and as it oxidizes, it physically expands. That swelling steel pushes outward, literally blowing the surrounding concrete apart from the inside. By the time you can see chunks of gray rock falling away from a bridge or a building, the damage is irreversible. The internal skeleton is failing, and the structural integrity of the entire build is compromised. This chemical flaw means almost every modern structure we inhabit is quietly deteriorating, acting as a ticking time bomb of internal decay that requires constant human intervention to stay standing. We have inherited millions of tons of legacy infrastructure that we must now maintain, ranging from aging naval breakwaters battling the tide to high-traffic highways bearing the weight of global freight. The stakes are incredibly high for critical defense structures like subterranean missile silos. These facilities cannot easily fail, yet their sheer volume and depth make them nearly impossible to replace once they begin to crumble. To keep these structures alive, we rely on a reactive repair model. Wait for a failure, dig up the road, and pour a temporary patch. This cycle paralyzes cities, burns through billions of dollars, and fuels a constant demand for new cement, an industry responsible for roughly 7% of all global carbon emissions. But we could choose to stop fighting this losing battle of manual repairs. Instead of reactive patching, we could engineer the materials of our cities to heal themselves. At Delft University of Technology, researcher Henrik Jonkers developed a way to give concrete its own microscopic immune system using living organisms. The recipe relies on an extremely resilient group of alkali-resistant bacteria called bacillus. These bacterial spores, along with a food source called calcium lactate, are packed into porous clay pellets and mixed directly into the wet concrete. These loaded clay pellets are distributed throughout the hardened concrete, acting as dormant biological reservoirs. They can survive in this dry, sleeping state for over 50 years, waiting for a breach. The activation trigger is the water that enters through a new microcrack. When moisture reaches the clay pellets, the dormant spores wake up and begin consuming the stored calcium lactate. As the bacteria metabolize that food, they excrete massive amounts of calcium carbonate, otherwise known as limestone. This biological output fills the void, physically stitching the crack shut from the inside before it can reach the steel reinforcement. Laboratory proof shows this biological mechanism achieves a complete watertight seal on sub-millimeter cracks. While standard concrete on the top remains dark and fractured, the bacterial specimen on the bottom is completely filled with new white mineral growth. Embedding a living biological process within the material allows concrete to function as a dynamic, self-maintaining tissue rather than a passive, degrading rock. Bacteria can seal surface fissures, but our most massive legacy structures require a way to transport these healing agents deep into the core over decades of service. DARPA's BRACE program is engineering bio-inspired vascular systems deep within aged concrete. Much like blood vessels, these artificial capillaries create a continuous transit network. When a fault develops, this network delivers healing substances directly to the fissure, neutralizing the threat before it reaches the surface. Vascularization bridges the gap between microscopic chemistry and macroscopic engineering, providing a way to extend the lifespan of our most critical infrastructure. Internal healing protects the skeleton, but the city still faces massive surface traumas. Biological concrete and vascular networks cannot fix a gaping highway pothole or a collapsed utility pipe. To handle those larger hazards, the University of Leeds launched the Self-Repairing Cities project. Their goal is to build an autonomous external immune system for the entire physical streetscape. This relies on perceive and patch robotic fleets, drone swarms that fly over active highways to autonomously diagnose and repair surface defects before they have a chance to expand. Beneath the pavement, fire-and-forget hybrid robots are designed to live indefinitely inside utility pipes. These units move through the network to conduct uninterrupted inspection, metering, and patching without human intervention. Deploying these robotic swarms allows the city to correct physical decay at its onset, entirely removing human workers from dangerous environments, like active roads and dark utility tunnels. We now have two converging scales of protection. Bacterial concrete maintains the city from the inside out, while autonomous robot swarms protect it from the outside in. Together, these technologies provide a path towards a significant engineering goal, creating the zero-disruption city by the year 2050. A city that heals itself avoids traffic-clogging streetworks while preserving the legacy infrastructure we cannot easily replace. By extending the life of these structures indefinitely, we significantly reduce the carbon burden created by the constant manufacture of new cement. Fusing microscopic biology with macroscopic robotics provides the tools to cultivate a resilient, living ecosystem that maintains itself indefinitely.